Hello, I am Mohammed Arashi and I'm going to talk about generalized inverses in linear modeling. I will record the videos in multiple sessions that you can download easily. Before we go to generalized inverse, it's better we recall the initial problem that we may face in the linear modeling. Suppose that you have such an equation, if you remember from linear regression modeling, and which x is n by m, beta is m by 1, and consequently y response is n by 1. From least square theory, I can estimate beta, and I denote it by beta hat, if x prime x transpose of x multiplied by x is invertible, then I can write the estimate with this guy. But what if x prime x is not invertible and we have rank deficiencies? Remember here, x prime x is of dimension m by m, and we have m parameters. So if x prime x is rank deficient and the rank is not equal to m, then it's not invertible. And in this case, we can approach generalized inverse. That's why in linear modeling, we need to know about generalized inverses. First of all, we start with the definition. And instead of matrix X for design, I use capital A. And instead of vector parameter beta, I use vector X here. So first we have this definition, a generalized inverse of a matrix A. Let me use this pointer, which is of dimension m by n, is a matrix A star such that x is equal to A star y. So if I come back here and x prime x is not invertible, so we can find the estimate of beta by the generalized inverse. So it is good to have information about generalized inverse. And it's a solution of a system of equation ax equal to y for all y for which the equations are consistent. I will discuss about consistency. We must know that in linear algebra, a system of equations, or linear or non-linear, not a problem, no difference, is called consistent if there is at least one set of values for unknown parameters or elements that satisfies each equation in a system. It means that I have a solution. That is the meaning of consistency, because in the following we need consistency. So we have this theorem. If I have such a system of equations, how can I find a generalized inverse? And what is actually a generalized inverse by means of linear algebra? In this theorem, we show that A star is a generalized inverse of A if and only if A multiply A star multiply A is equal to A. And in what follows, I will give the proof of this theorem. First, suppose that A star is a generalized inverse of A. If A star is generalized inverse of A, so we have this definition for that, and we can show that in the right hand side happens. The system of equations is given by Ax equal to Ai. I assume that I can write the matrix A as A1, A2 up to An. Each of them is m by 1 vector and is consistent. Since it is a consistent relation, so the rank of the left hand side is equal to the rank of A and Ai. In order to get a better idea about this equality for rank of matrices, I have brought this box here. when we have a linear system ax equal to b, I can consider the augmented matrix A and B. So I put B on the right hand side of A, and if rank of A is equal to rank of this augmented matrix equal to number of rows in X, then the system has a unique solution. So unique solution means a consistent system of equations. Since our system of equation is consistent, so it happens. It means that I have this equality. Therefore, X is equal to A star AI. Why? Because of this definition. So it's a solution of equations for each I, and I can write it A star A. So I multiply the left hand side by A, and if I multiply the left hand side by A, since A star is generalized inverse of A, it vanishes and you get AI. So we will have A star A equal to A, and the proof is complete. Conversely, suppose that we have this relation. We can show that A star is the generalized inverse of A. Now, conversely, we assume that A star is any matrix that satisfies this equality. It follows that I can now come up with this linear set of equations, so I can start from this guy. I know that if A star is the generalized inverse, I must have this relation. So I start with this relation to see whether it is a generalized inverse or not. So I will write A star y equal to x, and then I pre-multiply from left hand side by A. Remember, here I get A star A equal to A. So I will come up with A star. I have this A star A is equal to A. So this this component here simplifies to AX. But we know from the beginning that AX is equal to Y. So if we come back again to this definition, according to the definition, because of this relation, I can say A star Y is a solution for all Y for which the equations are consistent. And this consistency shows that, okay, this is a generalized inverse. Or better say, A star is generalized inverse of A. Now let's look at some examples here. Before we go to coding in R, it is better we look at some examples and see what we mean by generalized inverse. Then we will code it. For sure, the purpose here is not to find the generalized inverse by hand, but let's do a little kind of tiny computation by hand and see what we get. Suppose that A is a matrix of this form. And from this relation, AX is equal to Y. So I can multiply this A by X and equate it with Y, which is of dimension 3 by 1. Remember, X is 2 by 1 and Y is, 1 by 2, and Y coming again. If I write it just to make sure that I'm also on the right page, A is 3 by 2, X here is 2 by 1, and Y must be 3 by 1. So I can assume that Y is equal to Y1, Y2, and Y3, and I can also assume that X is equal to X1, X2. If I multiply, I will get this set of equations, and a solution can be obtained by X equal to this matrix Y, and I can conclude that A star or the generalized inverse is this matrix here. We must keep in mind, if A is of dimension 3 by 2, then I expect the generalized inverse is of dimension to be of dimension 2 by 3. So it happens here 2 by 3, and it's easy to solve this equation by hand, so I don't go through details and solve the equation. You know that you can easily pre-multiply the both equality with some numbers, then they vanish each other, and then you can easily get the results. And the system of equations are consistent if I have a solution here. You see, if I add these two together, let me erase these blue lines and use another one. If I add these two together, then I will come with the third equality. So it means that y1 plus y2 is equal to y3. And in this case, you will have a unique solution. So it's a consistent system of equations. We can also try to see this generalized inverse satisfies this equality. You can pre-multiply a star with a and post-multiply a star by a, then you will get a. But this is out of our tolerance. I mean, we don't want to do it by hand. Nowadays, we do it with softwares, and I rather prefer to use R. Because in R, in the package mass, there is a function called ginv, which is abbreviation of the generalized inverse, in order to calculate the generalized inverse of a matrix. So we install the library, and then we require the library. We define a matrix in this way. It's 4 by 3 matrix, so we have 4 rows and 3 columns, and I use by row true. That I can read this matrix as you can see here. And if I use ginv of A, then M is the generalized inverse of A. Here, according to our notation, M is A star. At the end of this session, I will run some R codes, and I will also explain about another generalized inverse which is unique. One thing that I must mention is the uniqueness of the solution. Now let's consider another example. Once again, the purpose is not to work out with these equations by hand, and we will use R, specifically R stereo software, in order to calculate the generalized inverse. But in this example, we see that, okay, we may have another solutions. Let's start with this A. And we start with this linear equation. So we start with ax equal to y. Once again, if you want to adapt our notation with what we have is common in linear regression modeling, we may say y is equal to x beta. So instead of a, I will use, it is common to use x as a design matrix. And instead of small x, we will use the vector of coefficients beta. In linear regression modeling. So if we can solve such a equation, then we can of course find the solution for this model. That's why we discuss about generalized inverse. Okay, if I once again use ax equal to y, then I have this system of equations, and the solution can be obtained by this way. X is equal to this matrix y plus this vector c plus this vector d. I'm not going to explain details of how we get this by hand. We're gonna use the machine to solve the problem and find the solutions. But this is the indeed we can find x in this way for any arbitrary c and d. At the end of this lecture for generalized inverses, I will explain about the general solution of this linear equation in this form. So we will understand how we will get such coefficients and such vectors. We must be patient, and we will get back to it at the end of the lecture note for generalized inverses. Now, if we, for a solution, we can set c equal to d equal 0, then the generalized inverse is given by this formula. Once again, the equations are consistent if I have this equality, and it follows that a star a is equal to a. And you can also try another solutions. You can change c and d and get another generalized inverse. It means that the generalized inverse is not unique. Even the other example, if you try the other example, you will see that the generalized inverse is not unique. There is another example, a little bit complicated one. Here we have 3 rows. So A is, it's 4 rows, but I say 4 here. 4 rows and 5 columns. So A here is 4 by 5, and the purpose of solving such an equation is not to do it by hand. That's why I emphasize we're gonna work with some R codes, and we don't want to solve it ourselves. If we write such an equation and patiently, for instance, we pre-multiply the first equation with 1/4, we pre-multiply the second equation by 1/3, and then subtract 1/6 of the first equation from it, and we continue this way. Finally, we will get to this equation for consistency, and a general solution is obtained by this formula. I will explain at the end why we have such a thing, and we need to be patient. Trust me, you will understand it carefully. One set of solution, or better say one solution for the generalized inverse can be obtained by setting C equal to D equal to 0, and this is the generalized inverse. And we can set another C and D, and suppose consider another C and D, and get another generalized inverse. So you see, once again, the generalized inverse is not unique here. However, we have this equality, and this is according to the main theorem, which says that if you pre-multiply and post-multiply the generalized inverse by the matrix, then you will get that matrix. This is the condition. Okay, now let's go with the other theorem. It is a nice theorem. Before I explain about a theorem, let's consider the implication of this theorem. This theorem says that if I have a generalized inverse B, then there is a correspondence generalized inverse of A if there is a specific relation between B and A. So once again, if there is a specific relation between two matrices, from generalized inverse of one of them, we can find the generalized inverse of the other one. But what is that special connection? Here in this theorem, we read that if P1 and P2 are two non-singular matrices, and define one of the matrices as you see, pre-multiplying the other matrix with one orthogonal non-singular matrix, and the other one from post-multiplying with another one, with multiplying with the first matrix, then there is a one-to-one relation which exists, and you can find the generalized inverse of A by this formula. So if B is defined by this formula, then you can find the generalized inverse of A based on the generalized inverse of B. So generalized inverse of B will give the generalized inverse of A, and according to this formula, generalized inverse of A can give the generalized inverse of B. So there is a one-to-one relationship. And here we're gonna explain about the proof. First of all, suppose that B star is generalized inverse of B. According to the first theorem, since B star is generalized inverse, so I can pre and post multiply B star by B and get B. Now let's write B from the definition. Okay, so we assume that this equality happens, and we want to find the generalized inverse of A. By assuming that this equality happens, we must also keep in mind that B star is the generalized inverse of B. Okay, I substitute B by the formula. So you have here, then the B star, and then the B once again. Once again, since these are non-singular matrices, we can say, okay, this P2 B star P1 A, I can write it as P1 A P2. Why it happens? Because P1 and P2 are non-singular matrices. So I can pre-multiply the left-hand side by P1 minus 1. So here we have P1 minus 1. I can post-multiply the right-hand side by P2 minus 1. Here I can write P2 minus 1. Then these two, better say, let me change the color. These two, it vanishes, this guy vanishes, you have this guy, you have this guy, so you will get this expression, which is what is remained here. In this case, now suppose, for a moment, let me get back the color. If I consider this guy as a new matrix, let's suppose it is a C. Then I have this equation A, C, A equal to A. Based on the first theorem, we call C as the generalized inverse of A. So the generalized inverse of A, which I show by A star, is equal to C. Now we write it here. So this guy is actually the generalized inverse of A, and I can write based on B star. So you will see the proof is complete. Conversely, suppose that A star is the generalized inverse of A. Once again, there is a relation between B and A given by this equality, and an A star which obtains by this formula is the generalized inverse of A. Now we want to see what happens about B. So we start with generalized inverse of A, and we have this equality once again. Now I substitute A star and from the definition. From definition, you can also write, excuse me, let me, sorry. We can, from this equation, we can come back and substitute the relation between A and B here. If I go up, I have this relation, and from this relation I can find A. I can say, okay, I pre-multiply, let's write pre-multiply left hand side P1 inverse. Remember, these are non-singular matrices. Here P2 inverse, then P2 inverse vanishes, these two vanishes, so I can conclude that A is equal to P1 inverse, B P2 inverse. Now I use it here. Let's go back with the same one. Okay, so I use A as this one, I use A here as this one, and we have A star, and it is equal to A, so we have this equality. So the second equality comes straight from the first equality. Then once again we pre-multiply the left hand side by P1. So I can write it this way, P1, and here P1, and post multiply the left hand the pre-multiply left hand side and post multiply by right hand side. So I post multiply by the right hand side by P2, and these two vanishes, so I will get B, and here these two vanishes, and I will get the rest, which is here. And once again, suppose this is another D matrix. So we have B, D, B equal to B, and according to the fifth theorem, I can understand that this D is actually the generalized inverse of B, which I represented by B star, and here D is actually P2 inverse A star P1 inverse. And this is the generalized inverse of B. So the proof is complete, and we learned that if we have such a relation between the two matrices, then we can understand that there is also a connection between the generalized inverses of the matrices.